few words, and then I can introduce our speaker, and then we can move on. So, President Chrysler, please, over to you.
Thank you very much, our able General Secretary. I think you have said exactly what I want to introduce, that we promise our general membership and sympathizers as well that we are well, will I say, seated to make sure that every month a minimum of a talk, and also maybe 2 or 3 as we read the terrain and see the needs for our members, especially for professional development and continuous improvement, as well as various contemporary issues that affect our geoscience fraternity and also our natural resources. So we are very, very privileged to have Lenka on the bill today, and it's not the last time that she's going to be around. And all those of us who have taken the time off their busy schedule, as well as my good self, just to make sure that we are seated to listen. We congratulate all of you, and we hope that this is not the last time, but you encourage other members as well to join us as we strive for our professional development, and also make sure that our activities as geoscience are carried out with best practice and also in the evolving market. So thank you very much, and all of you. And again, our council members who are on online now, we also want to thank all of them. We'll come back and wind up. Thank you very much, and have a good talk.
Thank you, Mr. President. I think I'll take the honors to introduce our guest for today. Lenka Barato is a research associate from the French National Research Institute for Sustainable Development. She is currently based in Abidjan, that is La Côte d'Ivoire. Her scientific research interests are focused on Precambrian geodynamics, with particular interest in the relationship between tectonic evolution and, please just a second, tectonic evolution and mineral forming processes by a multidisciplinary approach, integrating structural analysis, that is field and geophysical data interpretation, thermodynamic modeling, geochronology, and geochemistry. She has been working in West Africa since 2006 on various projects, including the WAXI project, focused on Precambrian paleogeography reconstruction using Mephic dike swarms. Lenka has been in this terrain for a very long time. She's worked in it, so she knows our terrain in and out. I have worked with her. In fact, she has even supervised my work a couple of times, right from my master's to my PhD. So she's well vested in our terrain, and the topic she's going to give is of interest to all of us, because at the end of the day, if we understand the geology and metamorphism, the mineralization that we are all chasing, we'll know exactly where to look at. And therefore, this makes her presentation one of an astute one, which I would want everybody to keenly pay attention to. And I think we have the participants also on board, almost nearing 70 people on this call, which is good. So Lenka Barato, please, your audience, Lenka Barato. So Lenka, please, you can take it away.
Okay, thank you very much. So can you hear me well? Is it fine?
Yes.
Perfect. Yes. Yeah. So thank you very much for this invitation. It's really a great honor, and congratulations for this initiative for the online seminars. This is really great, and I'm really looking forward to see more and more seminars online by this in the framework of your institute. So today I will talk about the structural geology and metamorphic evolution of the Birimian units in Ghana. And it's true that, as Prince said, it's been a while that I've been working in Ghana. Actually, my first trip to Ghana was in 2007 already, in the framework of WAXI 1, the first phase. And since then, we had several PhD students master students, in particular with Mark Jessell in the framework of WAXI. So here's a non-complete list of all the people who contributed to my talk. So what I will present today is also their work. Actually, they were our students, and yeah, we worked, as you will see, in many parts of Ghana. Yes. Yeah, so just a very short introduction to give you an idea why and what are we questioning in the Precambrian geodynamics. So there is a theory or a model which says that the Earth was much hotter in the past. So here on the two axes, these are figures from some papers, but they are more. You have the age at the right, and on the y-axis there is temperature, and you see that the temperature of the mantle is progressively cooling down through time. And at the same time, we can see it also, for example, at the metamorphic facies of the rocks. So you see here the white dots, they are Archean, so they are much hotter. They have much higher apparent geothermal gradient. The Phanerozoic rocks, which are black, they have much cooler gradients. This is taken from a paper of Michael Brown. So we suppose that the geodynamic setting or the tectonic or not mechanisms in the Earth evolved through time since the Archean towards younger days. And you see, you have here, this is another presentation of the same data. Basically, the granulite facies are red in this figure. High pressure granulites are orange. So you see a predominance of these hotter metamorphic rocks in the past, like 2.5, 3 billion years. And in the present, you have more these blue colder rocks. And the Eburnean Orogeny, which we look at in the West African Craton, is just a very interesting period, which is some kind of transitional period between the apparently very hot Archean times and the younger, colder present time. There are several models in the for the West African Craton in terms of tectonic setting. They vary from the kind of present day horizontal tectonics or plate tectonics to the subduction tectonics, like very old style, Archean style domes and basins of greenstones. And there are some alternative models, for example, by Dominique Chardon, who explains the structures that we see by some regional scale shear zones and high strain zones. And why is it important to study the geodynamic setting? As Prince already said, the practical outcome of our work is the application, for example, for the research of metals or gold or other metals. And you see in this figure that each particular geodynamic setting, like for example, continental arc or big arc, is associated with some specific type of mineralization. So you can have, for example, epithermal gold in continental arc. You can have volcanic massive sulfides in big arc. And that's why we are trying to understand actually the tectonic setting which operated during the Eburnean Orogeny, when these terrains were formed, and also when many of gold deposits and other type of deposits were formed in the West African Craton. So the West African Craton is formed of the Archean nucleus, which is 3.4 to 2.6 billion years old, and younger Paleoproterozoic terrains, which are accreted to that, composed of granitoids intercalated with greenstone belts and big sedimentary basins, which were dated between 2.35 to 1.9 billion years. And today, I will show you more in detail the results of the studies that we held in Ghana. So there were several PhD studies in northern Ghana, so Prince, Amponsah, Sylvain Bloch, and Zhao Feng. And then in central and southern Ghana, there was a PhD of Helen McFarlane, Stefan Perrouty, and now there is currently ongoing master thesis of Priscilla Maisie. So the northern Ghana first. What we have done first, this is the new updated map by Sylvain Bloch. I will then show you the comparison with the older map. But you can see actually there is a big granitoid domain. And in the central part, there's a huge domain composed of volcanic rocks, sedimentary rocks, volcanosedimentary rocks, and lots of metasediments. And this part is really, really heavily tectonically reworked by various folding, foliations, and shear zones. So first of all, we try to establish the stratigraphic column, and we suggest that the stratigraphy starts with volcanic lavas, basaltic lavas, tholeiitic lavas, which become more and more calc-alkaline, and then they are followed by some volcanoclastic rocks, volcanosediments, and sediments. And at the top of the part, there are some unclassified polymictic detrital sediments. At the first sight, they look like Tarquin-like, but they are not really. We have dated them, and they are older. And all of this series is intruded through whole time by granitoid intrusions of various compositions and types. You see, there are at least 5 types of granitoids here. So what we've done, how this map was constructed, we took field data. There was lots of field mapping, then the geophysical data and remote sensing data. So we had magnetic data, radiometric data, digital elevation models, gravimetric data, and Aster Landsat data, and which we calculated some principal component analysis, and we proposed a revised lithostructural map. So this is an EM, electromagnetic data, radiometric data for a part of the study area in northern Ghana. So we had all of these data for the whole area. Just some properties, typical properties of the lithological units in various kind of data. So for example, the granitoids, different types of granitoids look like this in magnetic data, radiometric data, and EM data. And this way just allowed us to propose an updated map. Here are some observations from the field, just to give you some ideas. So we could observe various phases of deformation. The very first deformation, which we call D1, which is shown as penetrative metamorphic foliation S1, which you can see in the first figure here. Then it was folded, for example, here in the second figure, by these S3 structures. And at some places, we could see the normal ductile faults in between the units, which we finally classified as the second phase. And in the end, there was more and more shearing deformation. So you could see some ductile shear zones, which were progressively cooler and cooler. Here you can more examples of these ductile shear zones, which were classified into third phase of deformation. And at the end, there were some brittle faults, and all these structural observations, which I will not show you here in detail, allowed us to define up to 7 deformation phases. So quite complex story. In terms of metamorphism, there were some really beautiful lithologies with assemblages composed, for example, of staurolites, garnets, kyanites, biotite, plagioches, and quartz. So very suitable for calculation of PT pseudosections. The PT pseudosections, they show some systematic trend. Actually, there is a quite cold apparent geothermal gradient at the early phases of the metamorphism, which is, you can see here, so about 500 degrees and up to 12 to 14 kilobar. And then subsequently, we observe some decompression and heating through time. And in the field, we saw more and more migmatitic rocks, some partial melting, which was quite predominant in the central part of the Bole-Bulanga terrain in northern Ghana. And overall, we can classify the metamorphic evolution as a clockwise PT path. Yeah, you can see there were several samples studied and calculated throughout the area. And in the end, Sylvain, he could establish this metamorphic map. So you have these green schist facies rocks around some core, which is composed of amphibolite facies up to granulitic facies and migmatites in the center. We could date these rocks using Uranian-led method on monazites, and these monazites, they were situating due to the textural positions in the tectonic scenario. So we could attribute actually them to D1 and D2, the deformation phase, according to their textural position in the metamorphic sediments. And the ages that we have obtained, they suggest at about 2.37 for the first peak D1 deformation and metamorphic phase, and 127 plus or minus 7 million years for the second metamorphic phase, which was associated to the D2 phase. So relatively quick exhumation and then some heating. And these ages are also consistent with the granitoid ages, which are about 2,120. There are lots of granitoids at about 2,120 million years in this area. So there was a huge heating peak, allowing lots of granitoids also to be in place. So this is synthesis. So you have a comparison of the new map compared to the Agie Duodu map from 2009. So you see already in the 1 million map, there are some shear zones which were observed, but we could refine these observations. And in particular, what we try to do is to associate the shear zones to different deformation phases. So there are different colors of the shear zones according to their age. And then as we had this sequence of deformation phases, and some of them were dated. Well, we could put them in the plot. So we could date this D1, D2, D3 by UPB. So these ages are very reliable. And then we see some later, more colder and more brittle phases, D4, D5, and D6, which occurred later. So about 2.1, 2.8 billion years. So another example is from southern Ghana. Here we did the same procedure, so interpretation of the geophysical data combined with field observations. So first of all, we have also suggested a stratigraphic column. So similarly to northern Ghana, the stratigraphy starts with lots of volcanic rocks. So there are basalts, there are gabbros, there are some volcanosediments, vulcanites, andesites, and they are intercalated with some sediments. And they are also adjacent to the Cape Coast Basin with lots of mica schists and volcanosediments. Then later, on top of that sequence, there were the sediments of the Kumasi group deposited, so lots of phyllites or volcanic sediments. And at the very top of the sequence, there are sediments of the Takwayan basin, so conglomerates, there are some sandstones and some phyllites. And throughout all this history, you have again intrusions of various granitoid bodies, deformed or undeformed, and various geochemistry. So you have here different types. So here is an example of the data that we use. This is airborne magnetics. This is airborne radiometrics. You can see very well the structures, for example, here in the Takwayan Basin. You can see the major faults even in the radiometric data, which is quite rare. And here are some observations, some examples of observations from the field. Again, I will not have time to show you all the details, but again, we could see some first penetrative metamorphic fabrics, which were folded by structures, which finally we called S3. And I will show you later what the D2 is interpreted as. So the first structures, as you can see, their orientation, they are mostly east-west, interpreted as north-south compression, very similar to northern Ghana. And then the S3 structures, they are mostly oriented northeast, so the northwest, southeast shortening. And then there are some later faults. You can also see the orientation of these structures in the map. So east-west structures in the Birimian volcanic rocks, and over, like in the Takwayan sediments, which are on top of that, you have the predominance of the northeast structures of the third deformation phase. We could do some profiles using the gravity data. So which showed actually the more deformed basement of the Ashanti greenstone belt, and on top of it, a little bit less deformed, but still folded Takwayan sediments. And one question that we tried to answer was, if we have these east-west structures in the Birimian sediments underneath the Takwayan units, can we see through the Takwayan units the magnetic signal of these east-west structures? So Stefan, he did some modeling using NODI, and indeed he could see actually that if the Takwayan units are not magnetic, you can see up to some depth the east-west signal of the Birimian units. And if you look at the data, actually, the real magnetic data, you can see some east-west structures within the Takwayan units, which in the field clearly show northeast trending. So that's quite interesting overprinting relationship. So the tectonic scenario that we have suggested, there's a deposition or volcanic eruption of all these basal series, which were deformed by the D1, which was north-south directed shortening. And then we have suggested actually the D2 extension. We didn't find actually in the field many extensional faults, but the presence of the northwest of the like huge amounts of sediments, it just suggests some opening of some basin which necessarily needs to be there, and then some again some shortening, so D3 shortening, northwest southeast oriented. And like in northern Ghana, we see some later phases which are more brittle, but important in terms of mineralization. You can see that the huge deposits in Ashanti belt were in place during these later deformation phases. So it's quite important. Yeah, so here's just a detail of the deformation scenario. And we have also done some metamorphic study. So we have actually started with Stefan Perrouty, but finally he didn't do this in his PhD. And we have took again his samples and did some extra field work last year with Priscilla Maisie. It's a master's student at Ghana University. So we went to the Damang mine again, because in Damang mine, Stefan, he could find some garnet, staurolite, chloride, biotite, muscovite-bearing metasediments. And also we have studied metasediments in the Winneba rocks. So they are actually metamorphosed at amphibolite facies conditions. They are bearing garnet, staurolite, muscovite, biotite, sillimanite. So we are currently calculating the PTC dissections, and I will show you the results probably next. And what's interesting in southern Ghana is the dating of these rocks. So we are planning to date these rocks, but for the moment, the ages that exist are only White et al. 2014. And interestingly, he dated monazites by microprobe, and he obtained very young ages, 2005. And if you do this table, they are much younger than the ages of the Damang gold